here's our example for project part 3. All right, so it's basically using what we already know. That is, we know the mass, we know the radius of our 3 planets, right? Planet A, Planet B, Planet C. And this time what we're going to do is we're going to use this, use that information, and we're going to calculate the escape velocity from the surface of the planet. Okay, so that's what this thing up here is talking about, with a distance of 1 radius from the center of your planet. All right, so that's in this case that's what R is. So let's say you're right at the surface of the planet. You know the mass, you know the radius. You can calculate the escape velocity. It's very simple. It's the square root of 2 times big G, and big G is the universal gravitational constant. Comes from Isaac Newton. Anyhow, it's 6.67 times 10 to the minus 11th. And then we can also calculate the acceleration due to gravity on the surface of your planet. And that value is big G times the mass divided by the radius squared. And so it's two things. The mass has to be in both of these equations. The mass has to be in kilograms and the radius has to be in meters. Okay, so that's what we're going to do. The first thing that you do is you're going to turn to the answers for part 2. So here, let me flash that. Okay, so here are the answers for part 2. You're actually interested in the mass and the radius. Okay, so you've got the mass and the radius of each of your planets. So you just you look up your particular look up your name, and then you'd look up this would be, for example, planet A's mass. That's planet A's radius. Anyhow, so and then you'd go to planet C. Planet B, and then you'd go over here. I gotta scroll over a little bit so you can see it. There's planet C. So you look up your name. Obviously, this is how you do it. You'd find your name in this column, in this first column, and then you just look. Okay, so anyhow, that's pretty simple. All right, so let's get to it. So the first thing I decided is let's do this for the Earth. All right, so and notice, of course, when we do this calculation, the velocity, the escape velocity, comes out in here. Let me make sure that you understand that the escape velocity is in meters per second. All right, and the acceleration due to, that's a G right there. That's supposed to be a capital G. The acceleration due to gravity is in units called meters per second squared. And we know the acceleration due to gravity on the surface of the Earth. It actually has a special symbol, and so the acceleration due to gravity on our wonderful planet is called little g. Little g. It's got its own symbol, and the value of it is 9.8 meters per second squared. Meters per second. I should have given myself more room. Meters per second squared. All right, so we're actually going to prove that right now. We're going to use these two numbers. All right, so there's the radius, there's the mass, and that's the radius and the mass of our planet Earth. All right, so let's calculate the escape velocity, which is let me think. It's about 11,500, something like that, 11,500 meters per second. All right, so let's prove that to ourselves. All right, so let's put the numbers in. All right, so our escape velocity is equal to, so it's the square root. Remember, you're going to use the values for your planet. All right, so it's always 2 times, and big G never changes. It's the same value across the universe, 6.67 times 10 to the minus 11th. All right, and then so this is the part where you look up what your mass is. Make sure your mass is in kilograms. All right, and so this would be 5.97 times 10 to the 24th. All right, so remember, you can write it this way as well: 5.97 e 24, right? Capital E 24. That's just another way of writing it. That's perfectly fine. And then we divide by the radius. But notice the radius here is in kilometers. But of course, that's a pretty easy thing to convert. There are, let me just indicate that over here. There are, 1,000 meters in a kilometer. So, 1,000 meters in 1 kilometer. That's an M. And so you just add 3 zeros to this, right? So that's pretty trivial. So this becomes 6371 and then 000. All right, so you just need a calculator to do this. All right, so I've got my calculator up here. So I'm going to put in these numbers and then take the square root. Okay, so it's 2 times big G, which is 6.67 times 10 to the minus 11th. You got to use this minus sign for this type of calculator. Times 10 to the minus 11th, and then times the mass of our planet, which is 5.97 e to the 24th, and times 10 to the 24th, and then divided by, so it's divided by 6,371. And, you could put 3 zeros, or you could say times 10 to the third, right? That's the same thing. And then you hit equals. Now, that's not going to be the answer. That's what's underneath the square root. And then, of course, you take the square root of that. Okay, so the square root is, there's the answer, right? So it's in meters per second. So here, let me write this down. So it's 11,000. You can round. So we're going to round it to one place past the decimal here. We're actually interested in kilometers per second. So this turns out to be, so it's 11,000. I'm sorry, didn't mean to make that go away. 11,180.5 and 80.5, and that's meters per second. And then to convert that to kilometers per second, you divide by 1,000, right? And so really the decimal goes 3 places to the left, right? And so here I'm going to round. So to round this, it would be 11 point. See, it would be normally 0.1, but there's an 8 after it. So rounding it to one place past the decimal, that would be 11.2 kilometers per second. All right. And if you look it up in different books, sometimes it's given as 11.5, but that's perfectly fine. 11.2 kilometers per second. That's the escape velocity to leave the surface of the Earth and not come back. Okay, so anything any lower speed than that, whatever the object is will slow down and eventually come back to Earth. All right, and just to let you know that speed, 11.2 kilometers per second, is close to 25,000 miles per hour, right? So that's a pretty substantial velocity. All right, so we're going to use these values again. So the mass and the radius in the exact same units, right? The mass has to be in. So remember, that's an E right there. It doesn't really look like an E. So I got it right here. 5.97 times 10 to the 24th. And then R, so you need R to be in meters per second in this equation as well. And so this is going to be the acceleration due to gravity. And the value that has been known since the time of Galileo, more than 400 years ago, the value is 9.8 meters per second squared. That's, established by the mass of our planet and the size of our planet. Okay, so let's prove that turns out to be 9.8 meters per second. All right, so that's, and remember, you're doing this with your 3 planets, so you're going to look up your mass in kilograms, your radius If it's in kilometers, you want to make sure you change it to meters using this conversion that 1,000 meters is one kilometer. All right, so let me set that up. Okay, so I've set everything up. Of course, here's our escape velocity in kilometers per second, 11.2. Of course, you gotta, in the assignment you have to do you do the answer in meters per second, right? So 11,180 point whatever. So put that, and then change it into kilometers per second. And you'll understand why you're changing it to kilometers per second in the next project. And then the acceleration due to gravity, we use big G. The mass has to be in kilograms. The radius has to be in meters. And I've set it up right here. So there's big G, 6.67 times 10 to the minus 11th times the mass of our planet, which is 5.97 times 10 to the 24th, and then divided by the radius of our planet, 6,371 times 10 to the third. Remember, that has to be in meters. And then don't forget, you have to square it. This is where a lot of people forget. You got to square that. And we already know the answer should come out to be 9.8, right? And it's such a special value that we get. It's got its own little symbol. Lowercase g is the acceleration due to gravity on the Earth, right? That's what this is supposed to say. Acceleration due to gravity for our wonderful planet Earth. All right, so let's go ahead and do that. All right, so there's the calculation for the last one. Remember, that's when you did that. Anyhow, all right, so let's clear that. All right, so here we go. So it's 6.67, and then you do times 10 to the minus 11th, so E, and I got to use this minus sign for this type of calculator. So there's 6 times 10 to the minus 11th, and then times the mass of our planet, which is 5.97 times 10 to the 24th, and then divided by, all right, so it's going to be 6,371 times 10 to the third, and then remember, you have to square that, okay? So this is the squaring part. There it is, squared, and then you hit equals to get what the answer is, right? And so we're expecting 9.8. And there it is, right? So 9.81. So, rounded to one place past the decimal, the answer, as you can clearly see, is 9. Let me write it right here, 9.8. All right? And that's exactly what we expected, 9.8. Here, let me get the calculator back up there. So, if you round it, so I think the assignment, they want you to just round it to one place past the decimal. All right, so that's project part 3. Again, you're doing this 3 times with that is you're doing it with your 3 planets: planet A, planet B, planet C, and you just look up in here. Let me show this one more time. So in the folder that says project part 2, these are the answers, right, that I came up with. Of course, you got to scroll over so you can see the numbers for the anyhow. All right, so those are all the numbers. Anyhow, all right, so that is project part 3.